Okay, so we're going to talk about principal component analysis. And the basic idea here is that we also, just like in clustering, we have data xi, I going from 1 to n, where xi is in Rp, so it's p-dimensional vector, just like in clustering. But instead of grouping these data points into clusters, we're going to try to come up with lower dimensional representations of these data points. And so let's think about what that might mean just from a visual perspective. And throughout this, we're just going to assume that it's centered. It makes our lives a little bit easier. So the xi's are centered, which just means that the 1 over n sum over I xi is equal to 0. So let's just assume that. Now, so visually, the way you should think about this is xi is in some high-dimensional space, which we will represent with 2 dimensions. Controversial choice. So we have some data set, and because it's centered, this data is going to be sort of grouped around the origin. Now, what does a lower dimensional space mean in 2 dimensions? Well, that's just either a 1 or a 0 dimensional space. And we're going to assume that this space, well, because it's a subspace and not an affine space, it passes through the origin. And so one-dimensional spaces are just spaces that are spanned by a single vector. So we're just really choosing a single vector that we're going to create a subspace with in that direction, and then we're going to project all of the data points onto that subspace. So let's think about this vector, and we might as well make it a unit vector. So if it looks something like this vector, then the subspace spanned by it would be everything that would be on this line here. Right. And then what we're doing, if we are projecting the data onto these, onto this space, the subspace, that means that we're going to take the data point and bring it to the closest vector that is in line with this subspace, that's on this subspace. Right? And so the points here that I've outlined, these are our depiction of the projections of these data points onto this subspace. Now, critically, if we think about these starred points, these are precisely the reconstructions of X using this low-dimensional space. It's still, the starred points are still vectors in 2 dimensions. And so you can, if you think about this in a compression context, right, we still have points that are 2-dimensional, but critically, they're in a 1-dimensional space, so they can be represented with just a single basis vector, right? And in general, if we're projecting into a low-dimensional space that's, say, k-dimensional, then we're going to be able to represent it with just k different basis vectors. So that's our goal, is to think about how do we learn these basis vectors? Because the choice of the vector that we selected that was along this line, this choice was that we used to span our subspace, that choice was by no means obvious. We have to select a way to choose it. So let's just think about this specific case that we're considering right now, and that's when we're just in a 1-dimensional subspace, and so W here is going to be the unit vector. So it is such that the subspace is the span of W, right? Such that W is equal to 1. And this W is equal to 1, if we scale the norm of W is equal to 1, if we scale the norm of W, if we scale W, then it wouldn't change the subspace at all. It would just make our lives, it would just create a something that was not identifiable from an optimization perspective. So we're just going to force the norm to be 1, so this is unit vector. Right? And so remember, currently this is for 1D subspaces. And we're just using this to motivate the larger problem of PCA. Right? Okay, so now let's think about the reconstruction. So our reconstruction, how do we find what this point is? Well, we know that W is an orthogonal basis, and so we can find this reconstruction of xi using, we'll call it xi hat, is equal to W transpose xi times W. Right? That's just our projection of xi onto the subspace spanned by W. Right? And then our error, we can think about the error of this reconstruction. It's our epsilon I squared is equal to, we'll write it as our 2 norm of xi minus xi hat, which is minus W transpose xi W 2 norm squared. So we're just choosing to use the Euclidean squared distance as our error. And that's the square of the size of this residual. So this residual is of size epsilon I, and this point here is our W transpose xi W. And this is our xi. Okay. So now that we have these things defined, we can think about minimizing our error. So because our W transpose xi W is a projection, then we get that we get a few things. So let's start with epsilon I squared. Let's just evaluate what this epsilon I squared is. Right? So let's just expand this out. So I guess instead of because, let's just write note that this is a projection. Not sure why this is doing this. Okay, so epsilon I squared, this is equal to xi transpose xi. So we're expanding out the square, minus xi transpose W transpose xi times W. So we have this, and then plus the square of this W transpose xi times W transpose xi times W. Right? Okay, but we know that W is a unit vector, so we can make a lot of reductions here. But let's first just keep writing this out. Minus 2, and now we have, we can write it W transpose xi times xi transpose W. For example, this is one way that we can write this, just by pulling this out in front, and then because it's a scalar, and then we have plus, we have W transpose xi, and then this element appears twice. We have the same scalar twice appearing, and then we have W transpose W. But this is 1, and so we have some things canceling, and so we get that this is equal to xi transpose xi minus W transpose xi squared. Right? So W transpose xi squared, let's think about this. So we're going to minimize with respect to W, this norm equaling 1, this sum over I epsilon I squared. That's how we're going to choose the W, which is going to in turn determine our subspace for PCA. And this is equivalent to maximizing over the norm of W equaling 1 of the sum over I of W transpose xi squared. Right? And that's what we've just shown, is that the argmin, so when I say these are equivalent, they have the same argmin. And that's really what we're trying to find, is the W. Right? So we're trying to minimize the sum of square errors, but this is equivalent to maximizing the sum over I W transpose Xi, subject to the norm of W equaling 1, right? The squared. Okay, so let's call this equation dagger. Okay, so that's what we've just shown. Now let's think about this new objective, 1 over n, sum over I, W transpose Xi, this whole thing squared. Let's think about this new objective. Well, this is equal to 1 over n, sum over I, W transpose Xi, Xi transpose, times W, which is equal to W transpose 1 over n, sum over I, Xi transpose, times W. Okay, well this should look familiar. Let's think about what the star is. So because the xi's are centered, the star is the covariance matrix. The empirical, so I should call it the empirical covariance, or the sample covariance matrix. Right? So we have that observation. Now let's think about what this is. So, well, first of all, the sample covariance matrix, we're going to note it with sigma hat, which is equal to 1 over n, sum over I, Xi transpose. And this is without a degree of freedom correction, which this is equal to 1 over n, X transpose X. And you should remember back from our ordinary least squares days, this is we talked about how the solution to ordinary least squares and the lasso and ridge all can be expressed using the singular value decomposition of this sigma. And that's going to appear here too. So all of that practice with singular value decompositions is going to arise again. Okay. So now this is still just the one-dimensional case. But let's think about this. That dagger, our objective, was equivalent to, so maximizing our objective was equivalent to maximizing the norm of W equaling 1 of W transpose sigma hat W. So this should look familiar to you. So this is one of the ways of expressing a largest eigenvector. So or a largest eigenvalue, right? So this is one of the forms for an eigenvector. So in this case, W is an eigenvector. Corresponding to the largest eigenvalue. Of the sigma hat. So this is our first observation, is that to find the subspace that minimizes that sum of square errors, that's equivalent to finding the eigenvector that corresponds to the largest eigenvalue of sigma hat. And so this is the one-dimensional case. And in the higher dimensional case, the story continues. So there's a number of ways to derive this, and the basic idea is that once we've found this largest eigenvector, then we sort of remove its component from all the xi's in a Graham-Schmidt type procedure, like we did with successive orthogonalization. Once we remove that from all the xi's, then we think about doing this procedure over again in sort of a greedy fashion, and that'll give you the second largest eigenvector. The eigenvector corresponding to the second largest eigenvalue, and so on. And so you continue to do this, and you think of this as building up your subspace from one dimension to your desired dimension, k. We're not going to get it too much into the details of this, and you're just going to have to sort of take it on faith that this argument extends to higher dimensional subspaces. So let's just recall the SVD. So let's recall a couple of facts about the SVD, called the singular value decomposition. This is X. We're going to write it as U d V transpose, where U d V transpose, U in general, this is n by n. D is actually rectangular in full generality. It's n by p, and V is p by p. So you can always write it this way. In ordinary least squares, typically we thought of p as being smaller than n. But in this case, let's just make it the most general SVD and make D be rectangular. So a rectangular diagonal matrix is going to have either a lot of rows that are zeros or a lot of columns that are all zeros, depending on whether n exceeds p or not. And then there's a couple of things. We have orthonormality. The U transpose U is equal to the identity. V transpose V is equal to the identity. We have that D is diagonal. So only the diagonal entries are non-zero. So DJJ is non-zero. Otherwise, DJK is equal to 0 for J not equal to K. Right? And so that means that if P is bigger than N, for example, then D is going to be a short and wide matrix. And so you're going to get a lot of columns at the end that are all zeros, because there's going to be no there's going to be no J such that J is equal to K. So that's how you should be thinking about this. And because it's rectangular, it's not going to be symmetric, obviously. And that's another thing to keep in mind here. So let's think about what the sigma hat is, because we want to find its eigenvectors. This is equal to 1 over n times x transpose x, right? And this is equal to 1 over n times u d v transpose u d v transpose. So we've done similar calculations like this before. So it's instructive to do it again. This is equal to 1 over n times the v d transpose u d v transpose. But of course, this is the identity. And so we get that this is equal to 1 over n v d transpose d v transpose. So so that sigma hat, this is the thing that we wanted the spectral decomposition of. We wanted the eigenvectors of this, because those were going to span our subspace. And we were using the ones with the largest singular values, or the largest eigenvalues. Right? And if you look at D transpose D is square with diagonals, which is D11 squared, which we're going to, I'll explain what's going on here, D33 squared, and so on, right? Where these are the diagonal elements. So D, I like to use lowercase for scalars, so DJJ is equal to capital DJJ in this case. What I did here is I just ordered them from largest to smallest. And we've seen this with ordinary least squares before, where we can just, without loss of generality, order these eigenvectors. And all we have to do is think about rearranging our spectral decomposition. Nothing about x changes if we rearrange this. And in general, our solvers are going to spit it out from largest to smallest. So that's how we can think about this. And these diagonals are the eigenvalues. Of sigma hat. It's D, is DJJs squared. So, so let's think about this. The eigenvectors, so conclusions, the eigenvectors of sigma hat are the right eigenvalues, or eigenvectors, sorry, vectors of X. Because if we look at our SVD, the right eigenvectors are the V's, right? And that's what remains as the eigenvectors of the sigma hat. And the eigenvalues are the squared eigenvalues of X, right? Okay. So that's helpful actually because we'll use this in the future, but the idea behind PCA is that we're going to choose our subspace by looking at the top eigenvectors of sigma hat and using that to span our subspace. That's the main goal here, following what we did in the one-dimensional case. Okay, so yeah. So let's also think about the reconstruction of X. So our X hat K, this has to be a lower dimensional reconstruction of X, or it's a reconstruction of X that is projected. So it's the X projected onto the top K eigenvectors. Okay, so there's a number of ways we can express this, but let's just think about it using the way that we expressed it in one of our homeworks. We have this U d sub k v transpose. This is one way to write it, where d sub k is just the diagonals zeroed out for all but the top k diagonal entries. d11, d22, and so on until we get to dkk, and then we have zeros. And zeros otherwise. So that's one way to think about this projection of xk onto the subspace. Now, how do we know that that's the case? Well, we said that x hat. So before we had that x hat I was equal to W transpose xi times W, and this was in the 1D case. The generalization of this is to choose the top K eigenvectors of the sigma hat, right? And then what this is in that case is we choose the top eigenvectors, which this is the P by capital K matrix of the top K right eigenvectors of X, transpose xi times our v sub k again. So this whole thing is going to be k dimensional, and then our v sub k is going to be here, written here. This is the way to express this using matrices. And let's make sure that everything works out. So this is K by P. This is P by, this is, I have it opposite. This is P by K. This is K by P. And this is P dimensional, so all of the dimensions work out. Okay. And so this is the higher dimensional. This is the k-dimensional case. The k-dimensional case. So that's x hat, the generalization of x hat. And so if we write this out in terms of x, the full matrix, this is capital X hat is equal to V sub k transpose times, this should be times so the xi, these are the rows of x, but they're in vector form, so we have to transpose this, and we also have to transpose our x. Right? And so this is equal to V sub k transpose V times D sub k transpose U. Right? So VK transpose V, that's just going to be the that's just going to form the identity matrix, except for in the top, that's going to be a matrix that looks like the identity, which is k by k identity, and then zeros elsewhere. Because if you think about the VK transpose, that's going to have rows which are eigenvectors, the top k eigenvectors, and then when you transpose it with V, it's just going to produce the identity because of orthonormality of the eigenvectors. But then it's only k by k, and so the other products are going to be 0. And sorry, this should be this shouldn't be square. It should be, let's see, this is going to be k by p, and so it should be short and wide, right? So ik and zeros there. So so we have this, and what this zeros, sorry, this shouldn't be d sub k, that should just be d transpose because we just plugged in x there. What the zeros does, the effect is zeroing out eigenvalues of d. So we can just write this as the same as equal to v d sub k transpose u, because if you look at what the d transpose times v sub k is, that's just ignoring the remaining eigenvectors in V, and d sub k, truncating the eigenvalues, has the same effect because these zeros are going to multiply those zeroed out eigenvectors, and so you might as well just leave the eigenvectors in there. So this is one way to think about it. You could think about it as instead making d sub k and v sub k be lower dimensional. That's another way to think about this. It wouldn't matter because those right eigenvectors get ignored anyway. So that's one way to think about this, but this is still going to be an n by p. Sorry, this is v transpose, so this is p by n. Yeah. So we can either make it so that another approach would be to make it so that you had v sub k, d sub k, a truncated version of d sub k transpose u sub k, where you only used the top k left and right eigenvectors, and that would be fine too. Then this would look like something that was p by k, this would be k by k, and this would be k by n. So that's another approach. I know that this is sort of, this is complicated. It's only complicated in the convention and the notation. It's not really complicated conceptually. Conceptually, you should just think about this as if we need to increase our k, then we're just going to, or if we want to project onto this k-dimensional subspace, then we're just ignoring the remaining eigenvectors, both on the left and the right. So that's one way to think about it. We can either do that in effect by zeroing out the eigenvalues in X, or we can do it by just only using k eigenvectors and eigenvalues. So that's the approach. Okay, so the result is that this x hat k So we'll write it x hat k. The result is that this x hat k is the best rank k approximation to x. And that's so another thing that we see. The result is that x hat k is the rank k k n by p matrix that minimizes the following thing, which is the sum over I of the norm of xi minus x k hat sub I. This is x k hat sub I. This 2 norms squared, and this is smallest amongst all rank k n by p matrices. Okay, so that's one thing that we end up seeing, right, from this. Okay, now how could we represent this x hat ki succinctly? So if we just write this x hat, and I'm just going to write x hat I, and we'll just know that it's k-dimensional. This x hat I, this is ui transpose d sub k v transpose. This is one way to write it. We've just selected the ith entry, where this ui is, it's not the eigenvector, it's the row of u. This is a row of u. We have to be clear about that. And this is equal to the sum over j of uij of this dk v transpose j, right? Where this j is indexing columns. So we have to be a bit careful about this. But this is the columns of this, and the ui is a row of u. Right? But what is this equal to? This is equal to the sum over j of uij times this d k jj vj, right? And this is equal to the sum over j going from 1 to k of this uij djj vj. Right? So I want to represent this x hat I using just k numbers. So one way that I can do this is by just memorizing the x transpose v, which is just going to give me this this part here. I could just memorize this uij times djj if that's what I want to do, right? And that's the only thing that's dependent on I. The rest are these v's here. Right? And these v's here are the are my basis vectors, right? These v's are my basis vectors. So this thing is just k numbers for each I. And so that's how we achieve some compression using principal component analysis. And so for capital K equals 1, we have that W is equal to V1, which is the column of V. I'll write it capital V1. And then we have that XI transpose V1, which this should be equal to Uij djj. Should be this part. This is the first principal component loading. PC loading. This is loading on the first principal component. And for k equals 2, we have v1 and v2 are the basis. The basis. And then we have that xi transpose v1 times xi and xi transpose v2 are the next PC loadings, principal component loadings, and so on. Okay. And now typically we think of typically we think of the principal components as being, or the principal component loadings as being these xi transpose vi, and then the reconstruction as being this xi hat. And so we can plot, for example, these different principal components here using against one another, and then we can get, say, for example, a visualization of a high-dimensional data set. Right? So that's typically one use of this principal component analysis. Now let's think about the algorithm to actually do this. So the first thing we need is to compute. So the algorithm is we need to compute our sigma hat. Needs to be computed, which is equal to 1 over n x transpose x after it's been centered, after the x has been centered, right? And then we need the top k eigenvectors and their corresponding eigenvalues, which would be or we don't necessarily need the top k eigenvalues, which would be lambda hat or lambda and v sub k of this. Now we know v sub k are these basis elements. So then we compute the loadings, which would be xi transpose v sub j, for I going from 1 up to n, and j going from 1 up to capital K. So the principal components have these loadings now, right? And to do this was p by p. So if p is significantly smaller than n, even if it's large, it still could be smaller than n. Then the complexity of this scales with k and p. The computational complexity scales somehow with k and p for computing these top k eigenvectors, and it depends on the eigenvector solver that you're going to use. And then when you want to do this matrix multiply, it's pretty cheap, because that just takes order n time for each of these, and so it's n order k times n, right? So the only thing that scaled computationally with n was computing these loadings, right? That was the only computational thing that really scaled with this. And now you have a low-dimensional representation, which are these loadings, a low-dimensional representation of your data.